All right, guys. I want to show you how a torque converter works and show you the different pieces of the torque converter, and I believe it'll help you make sense of some of the pieces of the transmission, and then, of course, how the power from the engine actually comes into the transmission and into the transmission input shaft. As you know, with an automatic transmission vehicle, we don't have a clutch pedal or a clutch disc like the previous class that we just finished. But somehow we've got to be able to still connect the engine power to the input shaft of the transmission. And so that is done with the torque converter, and there have been several design changes of the torque converter over the years, but overall, the basic design, the basic theory of operation has not changed very much since the very first ones in the late 20s. And so, probably the best way I've been able to show students how a torque converter works is to use a fan. So I've got an electric fan right here, and this fan is going to, when I turn it on, it's going to represent the engine's crankshaft. And the fan portion of it, inside of the torque converter, there's a piece right here that is the equivalent of that fan. And it's called the converter pump, not to be confused with the oil pump of the transmission. So this is the converter pump, and it is welded directly to the housing of the torque converter, and then we've got these big lugs that it bolts to the flex plate of the flex plate is bolted to the crankshaft. So if the engine crankshaft turns at all, so does this fan. So this fan represents the speed of the engine. And then down inside the torque converter, not physically connected to this fan, is a different fan right here that's called the turbine. And the turbine is what connects directly to the input shaft of the transmission. So if we can make the turbine spin, then we've got power flow coming into the transmission. Well, the trick is this first fan, the converter pump that we've talked about, or that I've introduced to you, sits right here underneath as far as this demonstration is concerned. And it's going to be basically blowing fluid on the other fan to make it or try to make it rotate. So that is what's called a fluid coupling. But I want to show you a few things about the fluid coupling before we get too far into the other individual pieces here. So this fan represents the engine. If I turn this fan to the lowest speed, I painted the back of the fan blades black, and I've got a phototachometer here that there's a little piece of reflective tape I put on the fan, and on low speed I can take this phototachometer and point it at the fan blade and get the speed of the fan off of that one reflector, and it is turning at 670 RPM approximately. So the engine is turning at 670 RPM. So now I'm going to take another fan But this time, this fan represents the turbine. This fan represents the turbine that connects to the input shaft of our transmission. And remember, the fan from the engine, which is the converter pump, has to blow fluid on the fan from for the turbine. Now, I've got this plugged in, but it doesn't, I'm not going to turn it on at all. So if this fan moves at all, it's because of the airflow, which represents the fluid flow inside the torque converter. So I'm going to put the two fans together. So I've got the engine fan turning. I have no physical connection between the engine fan and the turbine fan. And if I come in with the photo tachometer here, remember we had 670 RPM approximately over here. I've got 408 RPM on the other fan. So let me turn that off for a minute. If we have 670 RPM on the engine fan, but only 408 RPM on the input side, we've got some inefficiencies here. We've got some loss of engine power, engine torque, and that is going to decrease fuel economy. Well, prior to about 1978, that's how the majority of torque converters work. There was no way to physically connect those two fans together. They were allowed to slip. And as you drove down the road in your automatic transmission vehicle, all that slipping would cause what is known as fluid friction. And any type of friction, even rubbing your hands together, creates heat. And so the torque converter is the _1 heat generator in a transmission. And it generates the most heat whenever there's a huge difference, whenever there's a difference between the speed of these two fans. So if we can hook them together, then there's basically no heat generation, or very little heat generation. But if we allow them to slip, then there's a lot of heat generation. Now, who of you has ever sat at a stoplight or stop sign and you got one foot on the brake and you decide, hey, I'm going to race this guy next to me, so then you give the engine full throttle, but you still got your foot on the brake. So with your transmission in gear, that stops this fan from rotating. Because if this fan rotates, the vehicle's going to move. So one fan's vehicle speed sensitive, the other one is engine speed sensitive. But now you've revved your engine way up, and your engine can only rev up to a certain point. You ever notice that it only revs up to
4,000 RPM?
No, nowhere near that. 1,500, 2,000, maybe 2,500 RPM, depending on the vehicle. But if you put it in neutral, it revs up a lot higher. That's called the stall speed of a torque converter. Because the engine, trying to push the fluid through all of these veins, physically doesn't have enough power to rev any higher because of all this resistance of the fluid friction. So that's called the stall speed. The stall speed, there's an actual specification for stall speed for almost every vehicle, every transmission. It's a test you can do to see if it's working correctly. And there's other internal pieces of the torque converter that we need to talk about that can affect that stall speed. But anyway, think about that. If the turbine fan is stopped and your engine fan is spinning at 2,000 RPM, at that point you are going to create the most heat. And if you've ever read service information about a stall test, or let's say you're trying to diagnose an engine misfire and you decide, well, let me just load the engine here in the stall by 1 foot on the brake, 1 foot on the gas. Almost all service information tells you not to do that any longer than about 10 to 15 seconds. because, as it turns out, I heard one specification that the temperature increase in the torque converter at maximum stall like that increases 10 degrees Fahrenheit per second. So 15 seconds, you've got a 150 degree rise in temperature. Yeah.
Okay, I'm sorry, I'm really struggling with this idea of if things aren't touching, how are you generating heat for fluid that's designed to keep things cool anyway?
The fluid has to physically move through all of these veins and rotate back and forth. Fluid doesn't just flow freely. Every time it has to make a turn, there's fluid friction. Fluid has little molecules in it, and every one of those have to take a turn. So those molecules rub on each other, and it creates heat.
Thank you.
Especially under higher pressures and high speeds. Okay, so it's really bad to overheat your torque converter. Now, yesterday I mentioned to you that when all the fluid that leaves the torque converter immediately goes out to the cooler out there in the radiator or in front of the radiator to help cool it down. And then it comes back in where? Where does the I just told you. Where does the cooler fluid go after it comes back in from the cooler? It doesn't just drop into the pan, it goes to lubricate all bearings, bushings, and gears, and then it drops into the pan. All right, so normal operating temperatures of automatic transmissions are between, say, 180 degrees Fahrenheit, this is fluid temperature, and about 260, 270 degrees. And the fluids that are made for automatic transmissions are made to withstand that type of temperature. And so if we overheat the torque converter, some damage can occur even to the fluid. Even the latest fluids, they have a maximum temperature at which they'll start to break down. Or they won't break down until you reach this temperature. Now, fluids have to be a lubricant, they have to be a hydraulic, they have to act as a hydraulic. We can't have them rusting parts, we can't have it freezing. We're asking a lot of fluids. Well, if you took a transmission that was already warmed up, let's say it's at 250 degrees, and now you keep holding your foot on the brake and the gas at the same time, the fluid in the torque converter now can easily go over 300 degrees, which ruins the fluid. It doesn't necessarily ruin the transmission instantly. It can if you keep doing it too long and you don't give it enough cool down time in between. Most service information tells you to wait a couple of minutes to allow the fluid to circulate through the cooler to cool down. And by the way, most vehicles, the cooler is in the radiator. So what's the temperature of the fluid in your radiator? Well, the thermostat opens at 195 on most vehicles, so if that's cold to transmission fluid, think about it, transmission fluid is cooled in 195 degree water, or coolant. Transmissions run hotter than engine coolant, which some of the cooling fans on passenger cars don't come on until 230 degrees. So the cooler in the radiator can also be a warmer or a heater for that fluid in the winter time. So to help warm the transmission up, the heat can transfer from the warmer engine coolant into the transmission, and then the other way around when it gets too hot. But anyway, so you're sitting at a stop sign, foot on the brake, foot on the gas. Creates a lot of heat. It's very bad for the torque converter. If you've ever seen a torque converter that the metal has physically turned blue, that doesn't happen until around 700 degrees is what I've...
Really?
Yeah. So it's really been abused. Now, yeah.
What's, besides holding your foot on that and keeping the engine loaded, what is the usual cause of overheating the torque converter? Then too much weight on the vehicle?
Okay, yeah, and I'm just coming to that. So under what other situations, besides sitting there with your 1 foot on the brake and 1 foot on the gas, could this happen?
A really big boat.
Say again?
Towing that really huge boat.
Towing a really big boat or anything really heavy. Okay, so have you noticed that most trucks have a button on the end of the automatic transmission shifter called tow haul?
Yes.
The tow haul button, depending on which transmission it is going to prevent you from going into overdrive on most transmissions, or double overdrive, whatever it may be. It'll help keep the transmission in the range to where it's not loading the torque converter as much as it would normally. So what I'm saying is, well, let's take a different example, and then you can relate that to towing. Let's say you're just driving down the freeway in an empty pickup truck or passenger car, it doesn't matter, they all have torque converters with similar components and design. You're in overdrive, you're cruising down the freeway, and there's, let's say there's a truck or somebody going slow, and you have to slow down slower than you were driving or slower than the speed limit, and then you're stuck behind them, but then suddenly there's an opening and you can pass them. When you go to pass them, obviously you're not going to stick your foot on the brake pedal. You're going to mash the accelerator pedal clear to the floor, aren't you? When you put the accelerator pedal clear to the floor, the transmission is going to downshift. When the transmission downshifts, that'll allow the engine speed to go higher, which develops more torque, which is to help you accelerate around this vehicle or whatever it is you're trying to pass. But when that happens, vehicle speed didn't change. Let's say you're doing 60 miles an hour, suddenly you stomp your foot to the floor, you're still doing 60 miles an hour. The only thing that changed is your engine RPM went way up. Well, remember, this fan is vehicle speed sensitive, so it's still doing whatever speed it was to get you going 60 miles an hour. All of a sudden, the engine RPM goes way up, so this other fan suddenly goes up to pretty much the stall speed of the torque converter. So you could have a 2,000 RPM difference driving down the freeway between the speeds of the two fans in the torque converter. Just from passing someone. Well, that's passing someone, but now let's imagine that you're towing a trailer and you've got your foot down on the throttle more than you normally would with an unloaded vehicle because you're hauling however much weight. And especially if you're hauling too much weight, you're going to have to compensate for that extra weight by stepping farther down on the accelerator pedal. So if you step farther down on the accelerator pedal, it tends to kick you down to a lower gear, but it doesn't increase your vehicle speed. It only increases engine speed, which takes you to that stall speed again. Except this time, it's not just while you're passing. It's the entire time you're towing the vehicle, and especially going up a hill. So the tow haul mode attempts to try to prevent those situations. And on some transmissions, it actually watches fluid temperature, and if the fluid temperature starts to rise too much, it's going to lock those two fans together with a part called a torque converter clutch. And I'll show you the torque converter clutch here in just a minute. But we now have the ability, and have since the mid-70s, to hook these two fans together under certain situations with a torque converter clutch. And there's been various designs of that over the years, but the majority of them, it locks them straight together. The Allisons that we're working on here, it locks them together. It does not allow for any slip. The later model torque converters do allow for a little bit of slip because of OBD2 regulations that came out in '96. We have to monitor engine misfire by monitoring the rotational speed fluctuations of the crankshaft. Well, if your torque converter clutch is engaged, there were situations where you'd get a false P0300 engine misfire code because you would accelerate or decelerate with the torque converter clutch engaged, It's like driving a manual transmission and being in too high of a gear, and you give it gas or let off the gas, the whole vehicle just kind of jerks. An automatic transmission does a similar thing when the torque converter clutch is engaged, and it would actually fake out the crankshaft position sensors into thinking that there was an engine misfire. So their cure for that was to change the torque converter to where instead of being torque converter clutch, instead of being totally locked up, it would allow for a certain limited amount of slip. Somewhere around 45 RPM was pretty typical of what I've seen. So, enough with the electric fan demonstrations. Let me show you the actual pieces of the torque converter and how they relate to the transmissions. All right, let's start with just the basic torque converter housing like you guys have got out of your transmission. Just a reminder of what we talked about the other day. These flat spots on the torque converter match the flat spots of the oil pump drive gear. And so anytime this entire housing turns, it's going to turn the oil pump. So the oil pump housing actually has the front seal that keeps fluid from leaking out. It has a bushing in here that can't be any more than a maximum diameter, which there was a specification for that. There's a minimum diameter for this area here, and if that's excessive, it doesn't matter how good the seal is, it's going to leak anyway, because the seal can't hold any structural support. But if you've ever taken the torque converter out and tried to put it back in, it's quite a trick to get everything lined up and get it all in. Typically there are three things that have to line up, and I want to show you what all three of those things are. One of them is the flats of this oil pump. Sometimes it's not flat, sometimes it'll be grooves cut in this housing here, and there'll be little notches that fit right in the grooves, but this has to line up. So there's one of the three clicks as you try to put the torque converter back in the vehicle that has to line up. The other two, there's a part called a stator support, and if you look at your oil pump body, the stator support is sitting in your oil pump body, and Allison calls it a ground sleeve, and I don't want you to remove it. The instructions in our manual tell you how to remove it, but don't remove it. I removed it just to show you what it looks like, but this is pressed into this housing, and this housing is bolted into the transmission. This does not spin. This stator support shaft does not rotate. It just sits there solid. And so it has some splines on it that go down in, and it has to spline with a part called the stator. This is the stator support. It supports the stator. We'll talk about the stator here in just a minute, but that's the second set of splines that has to line up. And then, of course, your input shaft right here is the third set of splines that has to come in and line up with that turbine fan. So 1, 2, 3 sets of things that have to all line up as you put a torque converter in. Well, let's take a look at the parts in the torque converter that connect to these and talk about their function. So we've already talked about the converter pump. That's the fan that turns engine speed. So set that right over here. And we've already talked about the turbine, and it's the one that splines to the input shaft, and that's the one that turns, if the vehicle moves, if your transmission's in gear, if this rotates, the vehicle will move. If you're in neutral, this can rotate, the vehicle won't move. So that's the stator, the turbine. there's the turbine. On the back of the turbine is a set of splines. And I told you that in the mid-70s they started using a torque converter clutch. Well, the torque converter clutch is this big piece. And it sort of looks like a clutch disc in a way. We've got the rotational damping springs. We've got fiber material here. It looks like a giant clutch disc. But it has splined teeth right here that are going to hook to these splined teeth of the turbine. And so, let me set that over here. So it sits there and it turns with the turbine. And then that surface area, that flat surface area there, somebody's moved my sticker. That flat surface has to sit against what's called the converter cover. This part obviously is what bolts to the flywheel that hooks to the engine and rotates with the engine. But notice there's a nice flat surface right here. That nice flat surface is for this clutch disc material to be pressed up against. And when you press this clutch disc up against this converter cover, it physically connects the turbine, which was one of the two fans that we talked about, to this housing that is welded to the converter pump, which is the other fan, the engine speed fan. So the torque converter clutch is the part that hooks the two pieces together. But it does it by the way it's shown here, or oriented here. When it's down like it is, the converter clutch is released. This fiber material does not contact this flat surface right here. But when we want to apply the torque converter clutch, we run a fluid pressure on the back side of this, and it physically lifts it up. So that this can go up and down this way. When it comes up, it pushes solid against this flat machine surface here and locks the turbine, the whole turbine assembly, to this housing. And since, once again, since this housing is welded to this housing, which is our engine speed driven fan, the converter pump, that locks the two together. And when they're locked together, there is no heat generation, and it'll stop heat generation, and it improves fuel economy, because now we don't have that difference in speed. Remember, on the one fan we had what, 670 RPM, the other one was 408. So roughly a 262 RPM difference between the speed of the two fans. This would reduce that to 0. Now, a word of warning to you: the bolts that go into these lugs have to be the correct bolts. If you lose one of the bolts down the drain or whatever, you can't just go grab any old bolt and stick in there. Well, you can, but you shouldn't just grab any old bolt and stick in there. There's two problems with putting the incorrect bolts in there. One is it might be a different weight, physical weight, than the other bolts, which could cause a vibration, because this part rotates at engine speed. The second one is, what if it's too long? If it's too long, it'll thread clear into the bottom, you'll keep cranking on it, and it'll make a dent somewhere in this flat machine surface. And if it makes a dent in this flat machine surface, it's going to tear this clutch material off the torque converter clutch disc, and then you'll end up with the torque converter clutch that won't apply, and it will trigger all kinds of trouble codes that will lead you to diagnose that you need a totally new torque converter. And all of this material now has been run through the system. Now it's out partially clogging the oil cooler, transmission oil cooler. Another reason to flush the cooler. And then, so we can apply and release this. We apply and release it through, there's a hole right here in the end of this input shaft, this turbine shaft. And so if we send fluid up the center of that hole, it comes up in front here and pushes away, pushes down on this pressure plate as we look, clutch disc as we're looking at it. And then it flows through, comes back out another hole and goes out to the cooler. If all we do is reverse that flow, which is the job of one of these valves in this oil pump body, then the fluid wants to come into the hole here. So any fluid that was in this area now goes down the center of the input shaft. We build up pressure on the backside. This clutch material acts like a big seal, and it prevents any fluid from leaking through. So there's a valve there that just simply reverses fluid flow to apply and release the torque converter clutch. Now there's one additional part we have not talked about here in the torque converter. So let's get to it, and it's one of the most important ones. It's what makes the difference between what used to be called a fluid coupling and what now, with the addition of this part, is called a torque converter. It's this piece right here. It's called the stator. And the stator goes in between the two fans. So think of this as a piece that fits in between those two fans. The stator has a set of splines on the inside of it that is supported by, of course, the stator support. And that stator support doesn't rotate, it just sits there. But those splines versus the stator blades here have what's called a one-way clutch inside of it, which means it will rotate one direction only, but not the other direction. That's a one-way clutch. So it'll rotate this way, but not back the other way. And the purpose of this piece is to multiply engine torque. And this is the big difference that you'll get in power between a vehicle with an automatic transmission and one with a manual transmission. I've told you that if you had two equally equipped vehicles, same gear ratios, same engines, same everything, except one was automatic transmission and one was a stick shift, the automatic would out accelerate it and out pull it power-wise, as long as you could keep it cool. It's because of this piece right here. And stators can multiply engine torque anywhere from about the lowest stator multiplication factor I've seen is about 1.2. The highest I've seen is 3. So whatever engine torque is, you multiply it by that number, and that's what's delivered to the input shaft of the engine, but only under certain conditions. And it just happens to be those same conditions that overheat the torque converter under high load maximum stall, which is when you need the extra torque anyway. Yeah.
So, because torque is measured at the flywheel, like on the back of the Duramax and all the rest of the motors when they show torque numbers. So really, you can take that 765 or whatever the Duramax is, and what's the Allison's?
We'd have to look it up. It's probably 1.2, 1.3.
But you times that number by that number,
yeah,
and that's what's going through the transmission.
That's what's coming into the transmission. Yeah.
Oh my
yeah.
gosh.
And then you've got additional torque multiplication through the gear sets. Okay, so let's talk for a minute about how the turbine works, or not the turbine, the stator. What's so magic about this thing that it can multiply torque? Well, if we go back to the two electric fan example, we've got the one fan, which is the converter pump, blowing fluid on to the other fan, which is the turbine. Well, the fluid, if you look at these two fans, unlike those fans, it doesn't just blow through the fan and go away. It's going to come in towards the center, then it has to make a U-turn and come back out. I'm sorry, it goes the other way. It comes in here, makes a U-turn and comes back out on the inside. So it's making this constant loop between the converter pump fins and these fins. So that, as this rotates, centripetal force is going to have the fluid come to the outer edge and work its way back towards this one. But as the fluid hits it, it's going to cause this one to rotate, and then the fluid makes a U-turn and comes out the middle right here. Waiting right there in the middle for that fluid to come out is the stator. And the stator is going to take that fluid and make it pretty much make a 90-degree angle turn, and take that, and keep in mind this is pressurized fluid. It's moving rapidly and it's under high pressure, 60 psi or so. It's going to actually end up redirecting fluid. Instead of coming straight across from the turbine, it brings it on an angle, and the angle ends up hitting these fins in the direction, let's see, it would be this way, in the direction it's already spinning. So imagine this was spinning with the engine crankshaft, but now we take some high pressurized fluid and we blow it on these fins in the direction it's already spinning. What's it going to do? It spins faster. It spins easier. Just imagine taking one of those electric fans with an air nozzle, turn the fan on, it'll spin one speed, but now you hit an air nozzle at the right angle to it, the fan would speed up. That's what's happening here.
But that's not, is it called self-energizing? Is it making itself do it or no?
No. But this only occurs when there's a huge difference, or when there's a difference in speed between these two fans. So heavy acceleration, going up a hill, stuff like that, under those same conditions where it would overheat also. So it's not a permanent, always you have more torque, more power. It's only pretty much when you need it. And then the rest of the time, once these two fans pretty much catch up to the same speed, then the fluid that hits this ends up hitting it on a different angle, and then the roller clutch in there just allows it to spin freely with the two fans, the turbine and the converter pump anyway. So one more time, we've got two fans, we've got a stator in between. The stator, whenever there's a difference in the two speeds of these, will lock up on that stator support, redirect fluid to blow fluid on these blades, all at the same time, multiple nozzles all at the same time, helping this rotate in the direction that it already rotates. So a fluid coupling is basically a torque converter without a stator, and that's kind of a gutless dog. It didn't work out very well. It worked, but it just didn't have the acceleration that you would get once they came out with a stator. And I've seen some torque converters that have two stators in them and multiple pieces. They're the ones that end up multiplying the torque clear up to 3. Is the multiple stators. So a torque converter, and you'll need to know this for the ASE exam. Torque converter does 4 things. We've talked about all of them, but let's review them. The first thing a torque converter does is it drives the oil pump of the automatic transmission with those flat spots or notches on the front of it. The second thing is the two fans we talked about. It provides a fluid coupling. The third thing is we've got a torque converter clutch that can engage to improve fuel economy and reduce heat buildup inside the torque converter. And probably one of the most important things after fluid coupling, because the fluid coupling replaces the clutch disc on a manual transmission. The second most important thing is the stator that multiplies engine torque, which is the huge advantage of one of the huge advantages of an automatic transmission. All right, well, any questions, concerns? Yeah.
I do have a question, maybe you said this, but when the clutch is engaged, it was under what conditions that the clutch engages again?
The clutch will engage under the converter clutch, torque converter clutch will engage under low load conditions. So pretty much flat driving, not going up a hill. It'll stay engaged going down a hill.
So if you're climbing partways with the trailer on,
It
it's
will not be on.
disengaged,
Yeah.
and the stator is engaged doing its job.
The only other time I've seen them come on is if the transmission control module, the TCM that controls the transmission, detects that the transmission is overheating. It'll go into a overheating mode where it will lock up the torque converter clutch. Now these torque converter clutches normally don't engage until you're in overdrive, but sometimes they can engage as low as second gear, just depending on the vehicle year, make and model, and so on. But if you're overheating, it can keep this thing on clear down through second gear. Never do we want it on in first, because if you pull up to a stop sign and the converter clutch is engaged, that's like driving a manual transmission, pulling up to a stop sign and not stepping on the clutch pedal. It'll kill the engine. All right, well, yeah. All right, that's torque converters.